Great. So, in case you like homeworks, this is one more example that here we have that the genus is 2, and so the way you should view this genus 2 surface is that you take the blackboard and compactify it, so this is really the 2 sphere, and to that 2 sphere you attach 2 annulus, so basically just identify these 2 circles together and identify these 2 circles together as well. So now this is the genus 2 surface, and inside you will see some circles. So alpha 1 is an arc, but when you identify these 2 circles it's going to be a closed curve, right? And the same is true for alpha 2. Beta 1 is clearly a curve, and you can see that beta 2, it's, well, I guess it starts here, goes around here, comes out here, and then goes here, which is identified at that point. So eventually this is also a closed curve. And you can see that they are linearly independent. Alpha 1 and alpha 2 are linearly independent. Same is true for beta 1 and beta 2. And well, so that there is a 3-manifold associated to it. And there is also a parameter in this picture, how many times I do this twisting on this side. And so correspondingly you get some 3-manifold Yn. And I guess the question is, what is age 1 of Yn? It's going to depend on n. And note that the space of spin C structures is isomorphic to the second cohomology, which is by Poincare duality the same as the first homology. So what you will see that depending on n, well, that's cheating, right? Okay, so great. So there will be a few spin C structures depending on n, and I guess you could try to do everything in this picture. You will find the so you could find T alpha intersect T beta. That's easy. And then you can try to sort them into various spin C structures. So what are the intersection points that lie in the same spin C structure? And then you can try understanding the homotopy classes of disks connecting these points, and also the holomorphic disks that connect them. And there's an extra information that you can use, basically that you can position your base point anywhere in this picture. This is an extra thing that you can play with. And I guess if n is really large, I don't know, greater than 6 or something, and you are willing to move the base point in a sufficient location, turns out then you can compute the HF hat of this thing, I guess in any spin C structure, if n is big enough. So that's, I guess, an exercise, but it's also in one of our papers. It's in the second paper, which is holomorphic disk and 3-manifold invariance applications and properties. Okay. All right, so let me very quickly discuss some things that I tried to say at the end of the last lecture, but maybe we're too quick to do that. So something about periodic domains. And right, so here we have D that is in this form, some formal sum of some of the the domains in the complement of the alpha and beta circles. And so what is a periodic domain? Well, first of all, you can think of this as a 2 chain and take its boundary, right? You can take its boundary, which will be a 1 chain, right? Well, if it will be a 1 chain, then part of that 1 chain will be supported in the alpha circles, right? Boundary of D1 will have a part that's supported in alpha 1 in this picture, and some other parts will be lying in the beta circles. So I can decompose this 1 chain into, I guess, A1 plus AN plus beta 1, 2. Beta n, when these parts are part of this chain that are supported in the alpha I circles and the beta I circles. Is that okay? And the definition is that this expression is a periodic domain if boundary of AI is equal to 0 and the boundary of Bj is equal to 0 for all I and j. That's of course
A1 plus dot AG.
Yes, sorry. Yes. Of course, the boundary of this whole thing is always 0, right? But I want these things individually to be 0. And that means that when you really take geometric to the boundary, this boundary will be the union of some arcs with multiplicity. And when I put them together, I will get things that are cycles in the alpha and beta circles. So I will get boundaries with really going to be some multiples of the alpha circles and some multiples of the beta circles, right? So in this example, we have, I guess, D1 and D2. I'm sorry, D1, D2, I'm sorry, D1, D2 and D3. Somewhat larger picture that you can actually see. And in this example, the periodic domains are some number times D1 minus D2 plus some number times D1 plus D2 plus D3, which you can easily check. And then depending on where I put the base point, do I put it here or do I put it somewhere here, the periodic domains that will have 0 coefficient at the base point will be different, right? So if I put the base point here, then the periodic domains with nz equal to 0 are k times d1 minus d2, and you see that all of them satisfy this condition that they have both positive and negative coefficients. However, when I put the base point somewhere here, then this is no longer true, so then the periodic domains with nz equal to 0 will be of some form like some number times 2d2 plus d3, and then you will get periodic domains that don't have, say, negative coefficients. So this was an allowable situation, but this is not quite an allowable situation. Okay. Also, I mean, this periodic domains is really easy to study, and you can see that the periodic domains are in one-to-one correspondence with z plus h2y z, and this is basically the argument that we had last time. So if I have a periodic domain, this is a 2-chain, right? A 2-chain whose boundary can be written as a bunch of alpha and beta circles, and then I can fill in these alpha and beta circles with disks inside u alpha and u beta, and we get closed surfaces, and that's the correspondence to the second factor, and the first factor is use the base point, and the coefficient at the base point will give you the first factor, right? So this is the map going from here to there, which you can easily see it's an isomorphism. Okay? And also, surprisingly, periodic domains are in a one-to-one correspondence with, this is when g is bigger than 2, with pi to xx. And here the map going from here to there is, so this map f of phi is, just take the domain of phi. Okay, and the last remark, we had these weakly admissible things, right? And weakly admissible was something that, which is, if you have a periodic domain which is non-trivial, but or nz is equal to 0, then it has to have both positive and negative coefficients. So a reformulation is, that's also an easy lemma, that says that a heegaard diagram is weakly admissible if and only if we can associate a metric to sigma g so that for each periodic domain with nz equal to 0 satisfies, so what is this periodic domain? This has to have this form, sum of ai di, right? It satisfies that that sum of ai area of di is equal to 0. And sometimes, by the way, this expression we can call the area of this D. Okay? So, well, varying the metric is basically just to say in this case that for each domain di has to have positive area, right? So I'm going to associate some positive numbers for each di, and it turns out that I can then solve this this problem that all the periodic domains with this expression have 0 area, right? And of course, the backward is quite easy. If it has 0 area, then it has to have both a positive and negative coefficient somewhere. Okay, so now you see why this is a good condition, being weakly periodic, because okay, so I claim weakly periodic implies that if you take I'm sorry, yes. Weakly admissible periodic domain implies that if you have a homotopic, so then there are only finitely many homotopy classes here with nz equal to 0 and the moduli space is non-empty. Because this is exactly what you wanted, right? So, why is that? Suppose so suppose I have two such homotopy classes, right? Then I can take d of phi1 and I can take d of phi2. According to that proposition up there, I could associate an area function, I can associate a metric, so that all the periodic domains have zero area. Okay? Now I would like to use that. So first I can take d phi1 minus d phi2, and that's going to correspond to d phi1 times phi2 inverse, which homotopy class lies in pi 2 xx, right? And since nz of phi1 is 0 and nz of phi2 is 0, we also see that nz of phi1 times phi2 inverse is 0. So this is a D of a homotopy class connecting x to x. So according to some of the earlier stuff, this is a periodic domain. Right? But this is a periodic domain that has zero area, so this implies that the area of this is the same as the area of that. So this implies that all the homotopy classes that we are studying here have the same area, right? But that, which is a certain number, right, which could be really large. Nevertheless, all the homotopy classes that we are studying will correspond to expressions like that when you take their domain, right? And so we assume that all these homotopy classes support holomorphic disks, and that implies that all the AI are greater than or equal to 0. Well, since the total area is bounded, it means that all the AIs are bounded. So that means that we have only finitely many choices. Okay? Great. A hint for the homework that if you really want to study homotopy classes of disks, then this association going from phi to d of phi is really helpful. And it's much easier to think of down in the surface than upstairs in the symmetric product. And then you take this expression, then this is some linear expression in the surface. So maybe just a small comment on that, that when you do that, when you take the boundary of d of phi, then this is going to be relatively easy looking. So this is a 2-chain, right? So take the boundary and decompose it as before. But now we assume that phi is an element in pi 2 xy, when x and y are not necessarily the same. x1, xg, y is y1, yg, and I guess xi is an intersection between alpha I intersect beta I, but yi is an intersection of alpha I intersected b some sigma I, when this is this sigma is an element in Sg, right? So the claim is that that if phi is really a homotopy class connecting x and y, then when you take the corresponding 2 chain and take the boundary, then these 1 chains on alpha and beta circles have to satisfy some conditions. Namely, the condition that they have to satisfy is that the boundary of AI is going to be something yj minus xi, and the boundary of B, that would be some x, one of the x coefficients minus one of the y coefficients. So the way it really looks like, look at this example, was this square, right? So some time ago I said that there is a homotopy class connecting these points, is alpha, beta, alpha 1, beta 1, alpha 2, beta 2, x1, x2, y1, y2. And since this corresponds to a homotopy class, so this D is really the domain of some homotopy class connecting x to y, when you take it's 1 times they take the boundary of that, then the boundary will have a part that lies on alpha 1, and that will connect x to y, and other part of the boundary lies on beta has to connect y to x, and so on. Is that okay? So this is just an example. Turns out that this is an if and only if condition. So if I really have a homotopy class, then its domain has to satisfy these conditions. On the other hand, if I find a domain, a linear expression that satisfies this condition, then I can find a homotopy class. So that helps in that example.
What's the condition? What's the condition?
Well, so you are looking for, trying to understand homotopy classes going from a certain x to a certain y, right? Now, the condition is that you should be able to find a linear expression, sum of AI di, with the property that when you take the boundary of that, then you take the various parts of the boundary corresponding to the alpha and the beta circles, then when you take the boundary on the alpha, it's going to go from the x coordinate to the y coordinate, and when you take the boundary on the beta, it's going to go from the y coordinate to the x coordinate.
But you don't, I mean, the boundary of the AI is 0, or is that?
The boundary of, well, maybe I'm overusing that name domain, right? We had periodic domains, right?
Yeah.
And we have domain of a homotopy class. The periodic domain is a special thing that corresponds to the domain of a homotopy class where phi connects x to x. And this, understanding these periodic domains is the thing that you need to understand in order to say whether your heegaard diagram is good or not. Okay? Now, that's great. So suppose we already did that, and this is a good heegaard diagram. Now, like in this example, the first Betti number is 0. So unless n is 4 or minus 4, so for most n's. So we don't have to check anything. But I would still like to understand that supposing I have really 2 intersection points, what are the homotopy classes of these connecting them? And can I explicitly understand the holomorphic representatives of that? But for that, I'm studying this problem of having 2 intersection points, x and y, not x and x, right? I have 2 different ones. And I have 2 different ones, and this is the general case. I would like to understand the domains of homotopy classes connecting to x and y, okay? And that's why you have all these long conditions. And now, like in this case, you don't have the A1 would be this arc, right? Its boundary is not 0. Now, it's true that when you specialize this example to the case when x is equal to y, x is equal to y, then you see that the boundary of A1 has to be x minus x, which is 0, and then we got back this special case, the periodic domain. Sorry. Great. Now, being my last lecture, I have to speed up, so let me try to do that. Lots of things. Deliberately I was talking about CF hat, but now I have to tell you that there are other versions of these Floer homologies. The easiest to describe would be CF infinity. So CF hat is a chain complex that's generated by the intersection point where I guess x is in T alpha intersect T beta, and we want to avoid that subvariety Vz. Now, on the other hand, we have more generators when here x is the same as before, but I is an integer. So these are the generators, and we no longer want to avoid that subvariety. But we still want to understand how the holomorphic disk meets that subvariety. So the boundary map of xi, well, again, I want all the homotopy classes, so all the intersection points satisfying that, I guess, so fix your spin C structure S, then I guess here Sz of y is equal to that fixed spin C structure. You are going to look at homotopy classes going from x to y. Some numbers j less than equal to I. Okay, maybe it's slightly easier to write this. Okay, so Maslov index of phi is 1, and then you take the number of solutions on the moduli space divided by the R action, and you multiply it with y times I minus nz of phi. Does this make sense? Before, I was looking at special homotopy classes, those where nz was equal to 0, right? Now, I'm no longer doing that. I'm allowing any kind of homotopy classes, but we still sort of record that information in the boundary map, okay? And this is perfectly okay. When the first Betti number of the three manifold is 0, when the first Betti number is bigger than 0, then again, just as before, we have to use these special heegaard diagrams. Turns out, in fact, that sometimes you have to use a stronger admissibility condition than weakly admissible. There will be a strongly admissible version that don't have much time to write down. Basically, again, it's the corresponding thing, but you want to make sure that you are going to have just finitely many homotopy classes where the Maslov index was equal to 1. And that will depend somewhat on the spin C structure. So there is a similar easy admissibility condition. So we are using special heegaard diagrams, but then you can write down this. It's going to be a finite sum. It's a well-defined boundary map, and that's CF infinity. The corresponding homology is HF infinity. CF minus is a subcomplex in CF infinity. This is the subcomplex generated by xi when I is less than equal to, I is less than 0. And CF plus is the quotient complex Note that this is really a subcomplex, and this is because in order for the homotopy class to support holomorphic representatives, we have to have that this intersection with NZ is greater than or equal to 0, which means that the boundary map really lowers I, or at least doesn't increase I. So that's why it's really a subcomplex, and CF plus is the quotient complex of CF infinity and CF minus. So if you like, this is generated by xi when I is greater than or equal to 0. And clearly, just from the definition, you see that there is a relationship between these three things. So that and there is then a long exact sequence. And HF infinity, as it turns out, not a very interesting theory. In for any homology 3 sphere, it's going to be the same. So it's a remark. HF infinity. So if the first homology of Y is 0, then HF infinity of Y, then there's just a unique spin C structure, and the HF infinity of Y is going to be Z's and zeros. So it's true that you can define HF infinity, but that's not a very exciting theory. In fact, if you think about it, HF infinity is a theory that doesn't use the base point very much. CF minus and CF plus, on the other hand, uses the base point, and turns out that these are the interesting versions. So this is sort of the uninteresting. Sometimes as a stepping stone, it's still very useful just because you have this long exact sequence. And so there is an information hidden in these maps. What is the image of that here? That's very useful. But HF plus and HF minus is the main thing. Okay. Very nice. So what else? Well, grading. I do have the same group. Yeah, it's, well, it's... Hmm?
So not like in the usual homologies where you have this grading.
Oh, you mean there is a grading shift? Yes, that's true. But since I haven't I'm sorry, yes, it's true. Yeah, sure. But since I haven't discussed grading yet, grading. So let's think about S3 for a second. We have this special heegaard diagram, just one generator. So clearly, HF head of S3 is going to be just C, right? Well, what you may ask, in what degree? So so this is a special case, I guess. Y is a homology 3 sphere, in other words, the first homology of Y is 0, and the claim is that HF hat is a Z-graded theory, and in fact this Z lies in degree 0. So how to define the grading? Well, what is easier to define, what I could do right now, is the relative grading, and perhaps Peter will talk about the absolute one, but so if I have two generators, X and Y, in T of intersect T beta, note that this is a special case. H1 is 0, so that means that there is just a unique spin C structure, so each intersection point will lie in the same spin C structure. So these are just two intersection points. Then I can define the grading difference between X and Y, and that would be defined by taking the Maslow index of phi, where this homotopy class between X and Y, and Z of phi is equal to 0. So how about doing that for HF plus of Y minus or infinity? Well, there our generators are pairs, right? Xi and Y. So we have this extra I and J, but the grading difference between them will be again the Maslow index of a homotopy class, when here I want to use a homotopy class between X and Y with the property that NZ is the difference between I and J. And again, there will be a unique homotopy class with that property. You may remember that the space of homotopy class is Z plus H lower 2. H lower 2 is 0, so there is just Z different homotopy classes. Map to Z is given by NZ. So that means if I fix this number, there will be a unique homotopy class, and I can take the Maslow index of that. Okay? And it's important to note that where GR X I plus 1 Xi is going to be 2. That's a local computation. Basically, you can understand that homotopy class by taking the constant map and adding a sphere to that constant map. Pi 2 of the symmetric product is Z. You take the generator, and you can compute the Maslow index of that by evaluating the first Chern class of the complex structure on that sphere, and which is 1, and twice of that is that Maslow index. So this is something that somebody had to compute once, but after that it's just the same for every X. So if you want to understand, say, HF plus of S3, well, you're generated by Xi's, right? There's the same one intersection point here, right? So that will be X0, X1, X2, and so on. But I don't take the minus ones. And the grading difference here is 2. So you have this thing, and you get lots of zeros. And turns out that also lies in degree 0. This, of course, is the easiest possible computation because you don't really have to compute any holomorphic disks. You want to do something slightly more interesting, then you can compute that example. And again, that is sort of painful, well, relatively painful, because you have to explicitly understand homotopy classes. There are other ways to compute, So, in fact, I think it is very nice to make direct computations because you really understand the theory better if you try your hand at computing. But you don't want to do that all the time because sometimes it's really tedious. For example, you can look at some special three-manifold called Brieskorn spheres. So what are the Brieskorn spheres? Well, you need three numbers, P, Q, and R, that are relatively prime. And then you are going to write down an equation, x to the p plus y to the q plus z to the r, I hope, equal to 0. So that's in C3. Well, this is a complex equation, so when you do that, you get a two-dimensional complex solution with some singularity at the origin. And what you do is you intersect this with S5. So intersect it with the equation that x in absolute value squared, right? So basically you take this complex singularity and you intersect it with a sphere and look at the intersection. This is four-dimensional, 4 real dimensional, intersected with that sphere. It's going to be 3 real dimensional, and you can prove that this is really a manifold. Great. So this is the definition of the Brieskorn spheres, sigma p, q, and r. And you can compute its homology, for example. It's going to be 0. So this is one of these prime examples in this theory. And just one spin C structure, so it should be relatively easy. Good. So sigma 235 is the famous Poincaré sphere that is, I think Cameron was talking about, and sigma 237 is, well, it's more complicated, but still one of the simplest examples in that family. And in fact, if you work out this example, you will see that both of them, maybe with the opposite orientation, are in this family for various n's. But you can see that there are quite a few intersection points in that picture, and I think for sigma 235 you have like 19 different intersection points. So finding all the holomorphic disks between that 19 intersection points is somewhat tedious, if not downright impossible. So if you really do this example, you will see that making n really large or really negative simplifies your life a great deal. So it's just so much easier. But so if you want to compute the answer for this, then you may want to find some other methods. One other method that you can employ, and again Peter is going to talk about that in detail, is what happens when you take a knot and you're doing surgeries, different surgeries on that knot. And in fact, this example is basically taking the trefoil, the complement of the trefoil, and making different surgeries on it. But you vary n, you vary the surgery coefficient. And some things are easy to compute, and then you would like to you have to compare different surgeries. And eventually, you can compute, I guess, h of plus, for example, here will be z0, z0, z, and lots of zeros. So it will be almost the same as for S3, except it lies in degree -2. So it's not quite the same, but very close. And h of plus of sigma 237, it's going to be z plus z, 0, z, z. So after a while, it's going to stabilize, and after y is going to be 0. It's true for any homologous 3 sphere that for large degrees you will get these pairs of z's and zeros, and for very small degrees you will get just zeros. But in between you can get something more interesting, so in this lies in degree 0. Or you can compute HF plus of sigma 2, 3, 6n plus 1 or 6n minus 1, and basically we have a similar picture. So for 6n plus 1 you will get z plus z to the n and 0, z, 0, z. So turns out that there's a large class of relatively large class of 3 manifolds, large enough to contain all the Brice-Kohn spheres, when you can explicitly compute this Floer homology combinatorically. I think Rolf is going to talk about today about an algorithm, and perhaps András Németi is going to talk about some other aspects of computing these Floer homologies for special 3 manifolds. So if you are lucky and your 3 manifold is relatively easy to write down, then there are explicit methods to make the computation. Sometimes you can make the computation by hand, and for most of the cases it's a real challenge to explicitly compute these things. Okay, so what else? Well, I guess we are really, what we have done so far was just to define these various versions of Floer homologies for a specific heegaard diagram. And as usual, you have to do 2 things before this theory gets interesting. One of them is to find interesting examples. So you want to show that your invariant actually does something. It's not the same for any 3 manifold, right? And for HF infinity, we are really unlucky, and that doesn't do much. But the other versions, say plus, you can see it does distinguish different 3 manifolds. But of course, what you have to prove first is that this is really an invariant. So maybe I spent the last 10 minutes discussing that. So this would be a theorem which says that if I have 2 different heegaard diagrams like alpha 1, alpha g, beta 1, beta g, and a base point z1, and I get another heegaard diagram, everywhere I write primes, right? And what you would like to, and so the statement is, if the corresponding 3 manifold y and y prime are orientation preservingly diffeomorphic, or what's the same, homeomorphic, then HF hat y t alpha t beta z1 is isomorphic to HF hat t alpha prime t beta prime z2, and the same for plus, minus, infinity. In fact, you can say more. There are these long exact sequences between plus, minus, and infinity, for example. You are going to have a map from the isomorphisms will respect that long exact sequence, will commute with that long exact sequence. So any information that you can deduce from this long exact sequence will be also invariant, unlike these boundary maps between. And also you can prove with more work that this isomorphism is basically canonical. It's canonical modulo an overall multiplication by plus or minus 1. So how do you prove that? Well, what we really have to understand first, and that's not hard, is, well, here we have two different heegaard diagrams corresponding to the same three-manifold, right? So the question is, so how different are these heegaard diagrams? How can I connect this heegaard diagram to the other one? And for that, and there are some moves, heegaard moves, ways in which you can change your heegaard diagram but still get the same three-manifold. One is isotopy. You are going to move your alpha circles in a one-parameter family. So it's example. You create new intersection points, right? Or the opposite of them, right? Handle slide. This is a more drastic change. So the way you should think about this, that, well, there are the alpha and the beta circles, and right now I'm going to keep, say, the beta circles fixed, and I'm going to move the alpha circles. So in this way, don't care where the beta circles are, but here are the alpha circles, and I'm going to replace this alpha 1, alpha 2 pair, just going to replace this alpha 1 by another thing, alpha 1 prime, okay? And one way to look at this handle slide is that here is alpha 1 and here is alpha 2. And this is really a handle slide of one of the circles over the other one, say handle slide of alpha 1 over alpha 2. What you need for that is an arc connecting alpha 1 and alpha 2. So it will depend on this arc. This has to be an arc that disjoint from the other circles. And then what you do is, along that arc, you're going to push your circle closer and closer to alpha 2. You know that in a heegaard diagram, there's supposed to be this joint. So when you are getting really close, you know they cannot touch. But what you could do, and that is exactly the move, is when it gets closer, you are going to circle around alpha 2. Okay? So this is sort of sliding alpha 1 over alpha 2. So this is a nice picture. Alternatively, you can take alpha 1 prime, any circle, which is disjoint from the other ones, and satisfy that together with alpha 2 and alpha 1, they bound this pair of pans. Turns out that these two different notions, bounding this pair of pans or moving by isotopy and then doing this handle slide, is the same. And you can see it in this picture, right? This was the original alpha 1, and this is this alpha 1 prime, and you do get this pair of pans right here. It's easy to see that it doesn't matter whether I use alpha 1 alpha 2 or alpha 1 prime alpha 2. I will get the same three-manifold, and you can see it in this picture. Think about U alpha. In both cases, U alpha is really just the inside of that surface in R3, right? If I do this, then I build up the inside. If I use this pair, I can build up the same thing. So you can see that the handle slide does not change the three-manifold. Any questions? Okay, the last one is the stabilization. And in this stabilization, well, I guess what you're going to do is to take your original heegaard diagram and fix a point and make a connected sum with a torus. So you go from a certain genus to the genus is going to enlarge by 1, and in that last torus use a pair of circles alpha g plus 1 and beta g plus 1 with the property that they have a unique intersection point. Okay? Turns out again that this is well, this is of course a new heegaard diagram, but the same three-manifold. The way to see that is that in general when you take two heegaard diagrams and make a connected sum, that's going to be the heegaard diagram of the connected sum of the two three-manifolds. So now we are taking the connected sum of the original three-manifold with the three-manifold given by this heegaard diagram, which is S3. So you get Y connected sum with S3, which is Y. So that also corresponds to Y. Okay, so there are these three heegaard moves, and the statement is, I guess, that if they are really the same question, the same three-manifold, then I can go from one of the heegaard diagram to the other one by using these moves, and also, in addition, I could use a fourth move, which is basically just a diffeomorphism from sigma g to sigma prime g that moves some alpha circles to the alpha prime circles. Clearly that will not change our Floer homologies, this diffeomorphism. And I mean, sort of implicitly I'm also allowed to vary the metric on the surface. Metric was important in the complex structure. So great. As soon as we prove that the Floer homology is independent under all these moves, well, and on the position of the base point, turns out the position of the base point follows similarly. You could use heegaard moves that are far from the base point. Here, far, and in case of the Handel slide, far being away from the base point means that the base point is outside of that pair of pans. So if you can prove that a heegaard move which is away from the base point does not change the Floer homology, then you can prove that eventually the two Floer homologies are the same. So this is what you need to prove. A few comments. This is fairly standard. This follows from standard arguments in Lagrangian Floer homology. Stabilization turns out fairly easy for HF hat because there you can put the base point in the connected sum region, and then basically just want to, so in case of stabilizations, at least you see that you had some generators coming from this heegaard diagram, and there's just a unique way of extending them to this new heegaard diagram. Take X, G points here, and extend them with this, using this one last point, right? So basically you have the same generator set, but you want to prove that the boundary maps are also the same. Now, this is really easy when we are working the HF hat because I put the base point here. Turns out that will guarantee that holomorphic disk in the symmetric product will be just holomorphic disk coming from here, multiplied with a constant map right there. For HF plus it's much harder, but you can still do it. But then you have to analyze what happens when you change the complex structure in the connected sum, make it really large, and then you have to prove something non-trivial. For the Handel slide, that's more mysterious because then usually in Lagrangian Floer homology, the way you prove that, if you have two different pairs of Lagrangians, they give you the same Floer homology, is that you can deform one to the other one by some allowable one parameter family, and then you can prove that the invariant is not going to change in that one parameter family. So it is true that when you take alpha 1, let's say alpha 2 times alpha 1, That's a torus in the symmetric product. And you take alpha 2 times alpha 1 prime, that's also a torus in the symmetric product. And in fact, it's true that they are isotopic to each other. But somehow the way we set up these Floer homologies was that we really use the fact that every time we are studying this heegaard Floer homology, then the tori's are coming from product of circles down here. And you can clearly cannot go from these pairs in such a way. So in order to prove that the invariant was independent of, and doesn't change under this move, we have to look at pairings. So this will correspond to, instead of 2 Lagrangians, we had to analyze what happens when you have 3. So here this would be T alpha, this would be T beta, and here you can put alpha 1 prime cross alpha G. This is the third, right? And so you have T alpha, T beta, and T gamma. And basically, you want a map, say, from the Floer homology of T alpha.
Why is T alpha instead of T gamma?
Well, do you remember this admissibility condition? That was, we had to use that when the first Betti number of the 3 manifold was non-trivial. Now, it is true that maybe the 3 manifold we are studying, corresponding with alpha beta, is, maybe the first Betti number of that is 0. But alpha prime is going to, so when you do this, it's easy to see that the pair T alpha prime correspond to some G-fold connected sum of S1 plus S2. And the first Betti number of that is non-trivial. So you are not allowed to really make, so when you really do this, you want to be in an admissible condition, and then you do have intersection points. But I guess I'm really out of time. Turns out that you have, if you have 2 Lagrangians, that you have a Floer homology, but if you have 3, then you can define pairings between Floer homologies that eventually will give you maps between different Floer homologies. And turns out applying these maps in this case will allow you to at least give a map from the Floer homology that you started with to the Floer homology you get after the Handel slide. And then you have to prove this is an isomorphism, but at least you can start with having this map. Okay, so this holomorphic triangle will come up several times later, because this is important not just in proving Handel slide invariants, but also in the actual computations. When you would like to understand how the Floer homology changes when you make surgeries, turns out you have to look at these maps induced by triangles, and that also comes up when you study 4 manifold invariants. Thank you.